Yes.
Yeah.
Homogeneous catalysis is a case when the catalyst and the reactants are in the same state, same phase. Like atmospheric ozone breaks down into naturally, this is ozone O3 and it is breaking down to O and O2. This is called ozone depletion. An all-time famous reaction. It breaks down more easily in the presence of CFCs. I think you must remember
We
this
didn't.
word.
Okay. Yeah, I was gonna say we didn't do this then because I remember doing this.
Hmm?
Yeah, we didn't do this then because I don't remember ozone at least.
But anyways, you remember it from last year or from
Fluorofluorocarbons.
depletion is a major problem. Ozone depletion is a major problem. Now, CFCs, when we start their journey, this is chlorofluorocarbon. It breaks into giving a chlorine-free radical and a remaining compound. Now, chlorine-free radical is very active and it attacks ozone. It attacks ozone and ClO is produced along with oxygen. Chlorine radicals are regenerated. This is ClO and this is O. They combine to form O2 and chlorine-free radical is regenerated. Now, ozone is a natural protection for us. Ozone is a natural protection for us. What happens that once the chlorine-free radicals attack ozone, they convert ozone O3 into O2. This reaction is devastating because ozone is gone and oxygen cannot provide that protection. CFCs are made by humans, and this was a struggle to get aerosols in perfumes, in the sprays, and because they were very inert. So we were looking for these type of inert compounds. It was our success, but that made a problem because CFCs are able to stay in the environment for a long period of time. They gradually penetrate up in the stratosphere, and when they reach there, they attack ozone and they destroy ozone. This is the reason ozone has been badly damaged in many spaces, many places in the stratosphere. So let's summarize. Ozone is a natural protection. It is O3. CFCs are man-made aerosols. They are these are inert compounds and we made them. But when we throw them in air, like the life of a refrigerator is over or any other perfume has been sprayed in air, they gradually stay there. As they are inert, they do not get depleted by nature. They gradually penetrate in the stratosphere. And when they reach the stratosphere, they attack ozone and they convert ozone into O2. And this is the damage and ozone depletion occurs. Now, chlorine-free radicals are very active. These are the same chlorine-free radicals. You remember that when you are doing halogenation of alkanes, free radical substitution, there also chlorine-free radicals are very active. They're very active. Now, you have to copy this example.
Yeah, I did copy that.
Okay, good. So this is our first example. The title is homogeneous catalysis. What is homogeneous catalysis? When the catalyst
Of
and
the
the
same
reactants
state, reaction
are
of the
in
same
the
state.
same state.
Yeah.
Now see the second example. This is a reaction between iodide ion and S2O8 minus 2. This is a reaction between them. Naturally, if you look very carefully, they both are negative. So naturally, if they both are negative, they will repel each other. If they both are negative, they will naturally repel each other. So as they repel, the reaction cannot occur. So we introduce iron 2 ions to catalyze this reaction. Look at this Fe2 plus. It will first react with S2O8 and it form SO4 minus 2. Then we get Fe3 plus, which attack I minus, plus minus again, reaction occurs. Overall, the reaction occurs in this way. This is a very famous example of homogeneous catalysis. This is a very famous example of homogeneous catalysis. Now you have to
Wait, no,
copy this.
that's our wait. So how is this a frame example?
Sorry,
Iodine. What's S2O8 exactly?
S2 is basically thiosulfate with oxygen 8 molecule. And it is normally it is like a reagent. Iodine, you know, it's a halogen. It's a halogen, and S2O8 is a. Have you heard about the starch indicator famous thiosulfate reactions? They were last year also, when starch solution is in a beaker and we place a cross under the beaker and the cross disappears.
Yeah.
Do you remember that? Any core? Do you remember any core practical like that?
Will it store in a cross?
We put a cross or any printed paper under a beaker, and the solution gradually cloudy, and then
Yeah, no, I don't remember storing a cross. Like, yeah, no, I don't know.
So that is that type of reaction. Now you have to copy this screen.
Okay. Hello, sir.
Have you copied it?
Yeah.
So this is an example of This is an example of homogeneous catalysis. Now, when you work out the reaction without any catalyst, look at the size of the activation energy. But when you conduct the reaction in two steps, the activation energy decreases. Why activation energy decreases? Because now the reaction has two steps. In every step, positive and negative ions are there. Positive and negative ions are there. They mutually attract each other, and that is why reaction will be faster. You can also start the reaction with Fe3 plus, and then you will end again on Fe3 plus. This is why we call it a catalyst. Another famous reaction of homogeneous version is the oxidation of SO2 to SO3. SO2 to SO3. This is a reaction when basically the car exhausts are there, and this is possible that NO2 coming from a car combined with SO2 and it becomes SO3, and NO will go back to NO2. Now look at this reaction, why it is dangerous, because SO3,
Acid rain, yeah.
yes, could combine in this, giving acid rain. This is another example of homogeneous catalysis. Now give a heading, autocatalysis.
Autocatalysis. Yeah.
Autocatalysis is basically a reaction in which one of the product is able to catalyze the reaction itself. It occurs when a product of the reaction catalyzes the reaction itself. Normally, it happens with manganate 7 with ethane dioate. This is the reaction. In this reaction, the Mn2 plus ions, Mn2 plus ions are able to catalyze the reaction. So look at this thing, and this is a very important reaction in your course because it's part of the core experiment also, the core practicals. I think 13 perhaps.
We add 0.5 cubic centimeters of a 0.1 molar solution of potassium manganate 7 0.5 cubic centimeters of a 2 molar solution of sulfuric 6 acid and 1 cubic centimeter of a concentrated ethanodoic acid solution to 2 test tubes. We also add a few drops of manganese 2 sulfate solution to the second test tube. In the first test tube, the reaction starts off quite slowly, but speeds up as more and more product is formed. In the second test tube, to which manganese 2 sulfate was added, we can observe the violent formation of the gaseous product from the very start. Ethanodoic acid reacts according to the following equation. Manganese 2 ions catalyze the reduction of permanganate ions, which is indicated by the disappearance of the color in the second vessel. In test tube 1, the reaction is catalyzed by the manganese 2 ions being formed. This is an autocatalytic reaction because manganese 2 ions are products of the reaction and catalyze it at the same time.
Now, you have to copy this. Occurs when a product of the reaction catalyzes the reaction itself. You have to copy this example. This is screen.
Yeah. So I'll copy it now. 2Mn.
Have you copied it?
Yeah, copied it.
Yes, then can you hear me?
I can hear you. I copied it.
Good. So this was catalysis. So we completed our job. Look at the sketch for this chapter. The
Mhm.
concentration of catalyst increases with time. Initially, there is no catalyst. Reaction is very slow. When catalyst comes in the product side, it occurs, but gradually, when the reactants are finished, there is nothing to catalyze. When the reactants are gone, there is nothing to catalyze. So reaction will eventually slow down. So you have to copy this.
Okay, done.
Autocatalyzed reactions are generally slow in the start, but then they become fast. Now, I want to show you this part of the syllabus, that our core practicals. There are core practicals 13A and 13B, rate of reaction. Following the rate of the iodine propanone reaction by a titrimetric method and investigating a clock reaction, Harcourt-Esson iodine clock. Core practical 14, finding the activation energy of a reaction. Now, have you done these chemical reactions experiment in your lab?
The clock one, yeah.
You have done the clock one, right? And finding the activation energy. I will inshallah share with you this clock practical element, because presently what you should do, there is a paper, there is a practical related paper also, right? The third paper, which is involving the knowledge of lab.